In this video, we are going to discuss and define the concept of pH and pOH. So pH and pOH, of course, related to acids and bases. If you have an acid, we'll call that HA, in water, it will dissociate to produce H plus and A minus. So it will dissociate into its constituent ions. But of course, because the hydrogen ion, which is just a proton, because that's incredibly reactive, it does not actually form. The H plus ion will react with whatever's near it, typically water, to produce the hydronium ion. So more correctly, we would write this expression as our acid HA, and we would put that in water, of course, in aqueous solution. So HA plus water will produce the hydronium ion and its conjugate base. So our acid will donate a proton. The water molecules around it will accept that proton to form the hydronium ion. And then, of course, the conjugate base A minus. So generally, H plus, you can see that written, but more correctly, H3O plus is commonly written to show the dissociation of that acid. Now, so when acids dissociate, as we just mentioned, they produce H3O plus by definition. The concentration of that H3O plus in solution is incredibly important in chemistry, in biochemistry, in biology. Of course, your blood has a certain hydronium ion concentration, and if that hydronium ion concentration in your blood gets a little too high or a little too low, it can be lethal. And so and this can also affect chemical reactions and lots of different things. So studying the hydronium ion concentration is incredibly important. And sometimes the hydronium ion concentration is expressed as what we call pH. If you have a hydronium ion concentration in your solution and take the negative log of that hydronium ion concentration, we call that the pH. So the pH can be calculated by taking the negative log of the hydronium ion concentration. So the pH is nothing special. It's just a different way of expressing a hydronium ion concentration. And then we can also, of course, convert from the pH back to the hydronium ion concentration. If you have a pH and you want to convert that to a hydronium ion concentration, we just take 10 to the negative pH power, and that will give us our hydronium ion concentration. So for pHs, we generally consider anything that has a pH of 7, we call that a neutral solution. If a solution has a pH greater than 7, so 8, 9, 10, all 14 or higher, we say that it's a basic solution. And if the pH is less than 7, we say that's an acidic solution. Now, if you think about it, the pH, if the pH is low, that means the hydronium ion concentration is high. So that means that there's a lot of dissociation by the acid. So things like stomach acid, hydrochloric acid, these solutions of these will generally be very acidic and have high hydronium ion concentrations, as you can see here, which equals a lower pH. Things that have low hydronium ion concentrations will tend to have high pH, and therefore we call those basic solutions. So let's practice converting and calculating pH and hydronium ion concentration in these two problems. A solution of stomach acid has a hydronium ion concentration of 0.04 molar. Calculate the pH of that solution. And second, human blood has a pH of about 7.2. What is the hydronium ion concentration in human blood? Pause the video, solve these two problems, and then check your answers. Okay. So here we're given the hydronium ion concentration. Of course, That is in units of molarity. So I've taken my hydronium ion concentration. I take the negative log of that, and you should get a pH of 1.85. So this is a fairly low pH, which means that's a very acidic solution. Stomach acid is very acidic. Human blood has a pH of 7.2. What's the hydronium ion concentration? So here we would take the pH, we would take 10 to the negative 7.2. Since our pH is 7.2, 10 to the negative 7.2. And if we solve that correctly, we should get a hydronium ion concentration of 6.3 times 10 to the minus 8. That's a concentration, so please include units of molarity. pH does not have units. However, concentrations, we do have units of molarity. So please be aware of the units there. Now, when we talk about hydronium ion concentrations, we also need to talk about hydroxide ion concentrations, and I'll show you why in just a second. But let's look at pure water. Okay, here we have H2O, 2 molecules of water, H2O. Water can act as both an acid and a base. So if you have pure water, some of that water, a few molecules of water, will lose a proton, and some other molecules of water will gain that proton. In other words, a small amount of water is converted into hydronium and hydroxide because water will, to some small extent, deprotonate and others will be protonated. So water, to some extent, can be acidic or basic. We could write a balanced equation for that. 2H2O liquid produces hydronium and hydroxide. Now, let's look at this in a little more detail. Since this is an equilibrium, this will eventually reach equilibrium, we can write an equilibrium expression. The equilibrium expression is, of course, generally products divided by reactants, but we leave out any pure liquids or pure solids. So our equilibrium expression, we call this Kw, the W for water, would simply be Kw is equal to the concentration of hydronium in pure water at equilibrium times the concentration of hydroxide in pure water at equilibrium. So this would be our, what we call the ion product constant for water, or basically just an equilibrium expression for the dissociation of water. Now, it's been measured that at equilibrium, at 25 degrees Celsius, the concentration of hydronium ion is 1 times 10 to the minus 7 molar, and the concentration of hydroxide is 1 times 10 to the minus 7 molar. So those are equal. So think about that for just a minute. Pure water, the concentration of pure water is about 55.4 molar. It's obviously pure, so it's a very high concentration. At equilibrium, the concentration of hydronium and hydroxide in that pure water is 1 times 10 to the minus 7. So you do have hydronium ion and hydroxide ions forming in pure water, but their concentrations are incredibly low compared to that of pure water. But nonetheless, that's still important, and we'll mention that why. We'll show you in just a minute. So if we plug in these values, our concentrations, into our equilibrium expression, if we plug in these, the concentration of 1 times 10 to the minus 7 molar for both our hydronium and hydroxide, we can calculate the Kw value, which is 1 times 10 to the minus 14. So this is very, very small, which means water dissociates to a very small extent at 25 degrees Celsius. And again, our equilibrium constants have no units. They're unitless. So Kw, as we showed you, for water, of course, is equal to the hydronium ion concentration times hydroxide. And mathematically, Kw is equal to 1 times 10 to the minus 14. So if you were to know the hydroxide ion concentration, you could, in a solution, if you know the hydroxide ion concentration and you know Kw, you could algebraically solve for hydronium. If you know the hydronium ion concentration in your solution, and of course you know Kw, which is a constant, you could calculate the hydroxide ion concentration. So these two or if you know this formula, then you can derive these two. So what this basically gives us is the relationship between hydroxide and hydronium in a solution. Let's look at this one in the middle. In a neutral solution, a pH of 7, the hydronium and hydroxide concentrations are the same. If you add an acid to water, what happens to the hydronium ion concentration? Well, it's going to increase. Well, if the hydronium ion concentration increases, then the hydroxide ion concentration must decrease. So these are inversely related because remember, the product of these two must equal Kw, 1 times 10 to the minus 14. So if one goes up by adding an acid, the other must go down. They're reciprocally or inversely related. Let's say you added a base to pure water. If you add a base to pure water, the hydroxide ion concentration will go up and the hydronium ion concentration must go down. So this would be a basic solution. So our Kw expression, our equilibrium expression for water, it allows us to calculate and appreciate the reciprocal relationship between hydronium and hydroxide in an aqueous solution containing either an acid or base. So much as we express the concentration of hydronium ion as a pH, we can also express the concentration of hydroxide ion in a solution as what we call a pOH. Well, if the pH is the negative log of hydronium, then the pOH is the negative log of the hydroxide ion concentration. We can also, if we know the pOH in a solution, we can calculate the hydroxide ion concentration in that solution by taking 10 to the negative pOH. Let's take a look at a problem. A solution of stomach acid has a hydronium ion concentration of 0.014 molar. Calculate the hydroxide ion concentration of this solution and calculate its pOH. Okay, pause the video and try that problem. Okay, so here we have a very high concentration of hydronium. Our hydronium ion concentration, remember, in a basic solution, it's 1 times 10 to the minus 7. This concentration is much less than that, so we'd say it's an acidic solution. If the hydronium ion concentration is less than 1 times 10 to the minus 7, the hydroxide ion concentration must be higher than 1 times 10 to the minus, or excuse me, must be less than 1 times 10 to the minus 7. So that's what we would expect here. So let's calculate our hydroxide ion concentration. We know that Kw is equal to hydronium concentration times hydroxide. So we can algebraically solve for hydroxide, Kw divided by hydronium. And we know that Kw, our constant, is 1 times 10 to the minus 14. And our hydronium concentration is given as 0.014. So mathematically, we solve and we get a hydroxide ion concentration of 7.1 times 10 to the minus 13 molar. Again, that is, as we expected, much less than it would be in a basic solution, much less than 1 times 10 to the minus 7. Now we're also asked to convert our concentration of hydroxide into a pOH. So let's take a look at that. Our hydroxide ion concentration, we calculated that. The pOH is equal to the negative log of the hydroxide ion concentration in that solution. So we take the negative log of 7.1 times 10 to the minus 13, and we get a pOH of 12.15. Now, when you work some of these problems, you'll begin to see some relationships. The concentration of hydronium times the concentration of hydroxide are always going to equal Kw, 1 times 10 to the minus 14. You'll also find that the pH in a solution plus the pOH will equal 14, which is the negative log of Kw. So work some problems and you'll begin to get more comfortable with these and see some of these relationships.